Okay, my BC kids, we are looking at section 17.1 today, looking at polar curves and derivatives. Now, polar curves you've never seen before, so these are kind of cool. They make some pretty pictures. Some of them even look like flowers when we get done with them. So here's your story with these guys. A rectangular coordinate system is only one way to navigate through a Euclidean plane. Such coordinates as x, y, that's what we're used to, are known as rectangular coordinates. And they're useful for expressing functions of y in terms of x. Curves that are not functions are often more easily expressed in an alternative coordinate system called the polar coordinates. Now, one thing you have to remember about functions, to be a function back in the day, and this was stuff we talked about, I know, back in pre-calc, but if it's a function, it has to pass the vertical line test, right? That's all well and good and honky-dory, but what if it doesn't? What if you've got something that doesn't pass that? And that's what these polar guys, you're going to see that they definitely do not pass the vertical line test. So we're in a whole different coordinate system rather than the rectangular, Cartesian, whatever you want to call it, system that we're used to. In a polar coordinate system, we still have the traditional x and y axes. The intersection of these axes is called the old origin. We call it the old origin. In this one, it's called the pole. So when we're talking about, obviously, polar coordinates, polar systems, our origin is now called the pole instead. Similar to navigating on the unit circle, we can now get to any point in two-dimensional space by specifying an independent choice of an angle theta from an initial ray, polar axis, then walking out along that terminal ray to a specified amount r, a radius, in either direction. So although the angle is an independent variable, we express the point in polar as r theta. Now this is going to be important to us. So we're going to be looking at points in the polar system as being the radius times the angle, or comma angle. The radius comma angle. So the point to the right over here would be a coordinate 4 pi over 4. So I would be going out 4, that's my radius, this is 4 is r, and I would have an angle, and my angle would be, change my color here, my angle is theta. The angle comes from here. This is our starting place, just like it always is. So this is our theta, and theta would equal pi over 4. So the coordinate for this location right here, that coordinate in the polar system, would be the 4, comma, pi over 4. Now the thing about these polar guys is that that's not the only way for me to represent that coordinate. And that's where example 1 comes in. Find two equivalent polar coordinates for the point above, one with r being positive, greater than 0, and one with r being negative, less than 0. So let's start with the ones being greater than 0. All right, so I know I have to have my radius being positive, so that's my 4. It has to be a 4. I need 2 points. Now they need to be equivalent but different. This almost reminds me a little bit of coterminal angles. Do you remember them from back in pre-calc? Where you have to go in one direction for it and then the other direction, go a positive direction and a negative direction to get the angle. That's kind of where we're at. So think about this. If I were to go in a positive direction, starting at my starting place, which is always on the positive x-axis, if I go up to hit it, I'm going pi over 4. Well, that's the same as the original. So what I have to do is go all the way around again and hit it the second time around. Well, if I think about that, that's going to be pi over 4 plus another 2 pi. Right? I get one whole another circle around it. So if I think about 2 pi, that's 8 pi over 4. One more is 9 pi over 4. Here's my answer. An equivalent polar coordinate would be 4 and then 9 pi over 4. Okay, so that would be one way to get it. Another way to get it would be to start in our starting place, and then we're going to go in the negative direction with my angle. They didn't say anything about my angle being negative. They said my radius had to stay, my angle being positive. They said that my radius had to stay positive. So now I'm going to go in a negative direction to get there. That's all the way around pi and a little bit more. It would be like pi over 4 minus 2 pi this time. If I take a full circle and I take this chunk away, that's going to give me what's left, and that, my friends, is negative 7 pi over 4. That would be an equivalent coordinate. If I were asking you to graph this, that's what you would do. Now, there's 2 coordinates for positive. Let's look at 2 coordinates for negative. And the thing with this is kind of weird or interesting is that this negative is just saying that you're going kind of over in this direction. If you take that 4, this would be like a negative 4 situation. An r equals a negative 4. That would give me a location right about there. And so I'm looking at this thing and I'm thinking, well, where is that? And so if I have my circle, this whole thing is pi, and this would be a quarter more because it matches that spot right there. So this would be pi plus a quarter more. That's going to be 5 pi over 4. If I go in a negative direction to get there, then this would be 3/4 of the way to pi. So a negative 3/4 pi, 3 pi over 4. And the reason why these have the same location is because these negatives are just talking about a directional type of thing. So I end up with it being the same value as what this guy is here. They have the same value across the system. All right, so why use polar coordinates? Graphs that are not functions in the rectangular form, f of x can still be a function in polar form. Some of these curves can be quite elaborate and are more easily expressed in polar form rather than rectangular form. They use GeoGebra to look at these pictures. I'm going to show you how to do this on your calculator. What else was I thinking I wanted to tell you? Oh, this is all coming and building towards, if you take Calc 3, you're getting into three-dimensional calculus at that point with Calc 3, that one of the next topics. Remember, this is our last unit. Don't cheer too loud. But our last unit, 17, 1, 2, and 3. But this is useful for the next step of calculus, which is going to be your Calc 3, which is three-dimensional. You get into three-dimensional stuff, which is not only the x and y plane, it adds in a z, a third dimension to this, and is really useful for people that make like MRI machines and those types of things where you need 3D pictures, or like architecture and drafting and such. So when you need a 3D picture of something, that's what we're talking about, is this calculus stuff. So let me show you on the calculator. We're going to just do the first one on the calc. I have to graph these. So I'm going to graph r cosine of theta. That's going to be our first one. All right, so let me tell you first what you want to do. Turn your calculator on. Go to the home menu and hit the mode button next to home. See that very top guy where it's flash and function? If you hit the right arrow on that, I think I showed you this for parametrics when we did the parametric section, you're going down to number 3 polar and press enter. You have to press enter twice. Okay. So I'm going to put in my y equals the cosine of theta. Now, you have to literally use theta. So let me clear it out because I had it in here. I was playing with it a minute ago. I'm going to do cosine, second cosine. And then theta is where the pi button is. So you need the green button and then the pi button, the caret, and then close the parentheses. So you literally are using theta in this. So do that. Now sometimes they might ask you to do this by hand. So I'm going to pause the calculator for a second. And if I have to do it by hand, this is the cosine function. So let's think about values for my cosine. So if my theta, it depends on what the angle is, what would the radius be? Because that's what I'm graphing. So usually you start at 0, write the origin, the pole in our case. And if I put the cosine of 0, we know what the cosine of 0 is, right? We go to the unit circle, we think about the coordinate, it's 1, 0. Cosine is the x value, so it's 1. If I put in, pick pretty things, don't make it this harder than it has to be. If I pick pi, The cosine of pi, that's at 90 degrees, so that's going to be 0, 1, so my cosine is 0, the x value. If I pick the next one, it's pi. If I go to pi, the coordinate is -1, 0, and that gives me a -1. Let me show you how this works on the calculator. We can do more, obviously. Well, let me talk about what more would be when I get to the picture. All right, I'm going to the table. I'll go there first. And let's make sure we're right. If we put in a 0, what comes out? 1. If we put in pi divided by 2, oh, I didn't put it in, I'm just trying to be too quick. If I put in pi, clear, pi divided by 2, that gives me 1.57, that gives me 0. And if I put in pi, that gives me -1. So my table's correct as I put them in there, okay? So you're putting them in the table, you can make sure that you're correct, you got it right. Well, let me go to graphing this. Oh, hold on a minute, let me fix my window here. I want to go from 0 to... I'll talk about this table and the window in a second. But here's what the whole picture looks like. Darned if that doesn't look like a circle. So when I look at this, so it's a circle, and what's the radius? The radius is 1. So when I go to my paper and I draw this, it starts here, comes over here, goes around. Now it doesn't matter which of these bullet type things that I use, and it does not. I'm just doing it kind of small here because look at what this one's going to be, 2, this one's going to be 3, and I want to make sure I give you some space on how the difference would be. So I'm going to make mine relatively small going inside of there. Now if you had to graph this, you would start with the coordinate 0, 1. Well, that's this guy over here. And then it goes to, when it's pi over 2, it goes to 0. That's this point here. And I'm going to show you how this looks in a second. Then when I go to pi being -1, it's kind of a directional thing that your radius is going to be 1. You know the radius is 1. So this one is now going between the pi over 2 and pi would be here. And you're graphing that bottom part of the circle. If you weren't sure if this were like on an exam or something like that, you can play with the window. So the first part of the circle started at 0 and went to pi over 2. I want to know what it's doing between these two so I can connect those points. So what I'm going to do is hit the window, and I want to know if the x-min is 0 and the y-min is pi over 2, pi divided by 2, that's helpful. Pi divided by 2. Just change the theta min, you can't really see it, here we go. Theta min to 0 and the theta max to pi over 2. Let's see what the first bit of this thing looks like. All right, we're going to graph it. Oh, it's the top of the circle. There you go. If I were to want to know what it's doing from pi over 2 to pi, the next section of this thing, I'm going to go back to my window. I'm going to change it to pi over 2 and pi. X min, X max. And then I'm going to graph it again, and that'll show me what the bottom part looks like. And there you go. You got the bottom part of the circle connected. So that the whole thing, it only takes 0 to pi to make this. If I were to keep going in my table and say, all right, well, what is it at 3 pi over 2? If I were to keep going. At 3 pi over 2, we know cosine is back down on the 270 mark, so it would be 0. And if I wasn't sure, I could put it in the calculator, but it is. If I want to graph this thing, change your window again, from pi to 3 pi divided by 2, and graph that, lo and behold, it's the top of the circle again. It's just going to keep going round and round and round and round and round and round until you want to stop. It's one of those spirally type things. So we can stop at pi because that gives us one complete picture of what this looks like. So one of the things that we're going to make note of is to get a full picture of this, how far do you have to go? And so kind of like a domain issue, for all of these with sines and cosines, it's only going to take us, and I'm down here in these patterns that you notice about this, that to make a full picture, I will say a full graph of this thing, this one you only have to go between 0 and theta being between 0 and pi. That's going to give you a full picture of what these look like. So that's a long explanation. Here's what we're going to do for these others. We're going to just, I'm not going to do all of them, but I'll do a few here. If I do, go back to your white, and let me put my window then back into 0 to pi, because if it only takes from 0 to pi to do this thing, that's going to give me a complete picture. Okay, so y equals, I don't want the cosine of theta anymore. I want 2 cosine of theta. A lot of times your calculator likes the time symbol in there. It should do it without it, but sometimes it's a little funky. Theta, I didn't have to retype that whole thing. I could have just changed that coefficient, right? All right, so let's graph it. Oh, there you go. You got the picture. It's a little bit bigger. So I'm going to put it on my page here. On my page, I've got, here it is, a little bit bigger. Right? So this would be 1. This would be now 2. What's 3 going to do to it? Well, you know 3 is going to make it even bigger yet. Here's the top of my circle. Here's the bottom of my circle. There you go. There's 1, 2, 3. 1, 2, and 3. How about if it goes negative? Maybe we don't know what that's going to do. So let's try that guy. If I put my y equals and do, change this to a -3 coefficient. Oh, cool. Still a circle, but look where it is. It went the other way. The radius took it to the other side. Still the same circle, though. All right, so that's this guy over here. Okay, again, 1, 2, 3. How about the sine? All right, let's change this totally up. Let's go to our y equals and change this to the sine function, just plain old sine. The sine of theta. So look where that lands. It lands along where the cosines were landing along the x-axis. Now the sines are landing along the y-axis. So it's a circle, still a circle, little guy right here. All right, what's 2 going to do to it? Well, 2 is going to make it bigger, right? So now it's going to be, maybe this is 1, this is 2. There's my there's bad circles, but you get the idea. What's 3 going to do to it? Make it even bigger yet. Circle along the y-axis. Whoop. There it is. What's negative going to do to it? Negative's going to throw it in the opposite direction. So instead of it going up like this, it's going to be down here. Again, all of this can be proven if you put it on the calculator. So what patterns do we notice? Well, they're all circles, right? We know that the cosine is on the x-axis. And we know that the sine is on the y-axis for these guys. And it takes pi to make a full picture for this one. Okay, that's all I can tell you about those. Let's flip the page and we're going to try some others. So these say, again, graph these on GeoGebra. We are not going to graph these on GeoGebra. We are going to look at our calculator. So this time I have y equals, I'm going to go up, I have 2 plus 2 times the cosine of theta. Okay, so here it is in my calculator. I am going to graph this thing. All right. Now this one's a little bit different. This one it actually takes, because now I've got other numbers involved. The beginning of this I can see, now these are sketches, kids. These are not necessarily perfect. So I can see that it goes like this, right, from my picture on my calculator. That's not a complete picture, right? The other one, it's like an enclosure. You're trying to make this an enclosure. So it must be that my window is not enough. Now, if I went from 0 to pi, What do you think might be the window that I want for these to get a complete picture? This did not give me a closed figure, which is what I'm looking to do. It gave me half of a closed figure. So if I'm going to do this, I want to now go to 2 pi. So I'm going to change my window. The 0 still stays the same, but I want this guy to go to 2 pi. I put that in. Here it goes. Graph it. Oops. Clear, escape, escape. I want to go y equals, there it is, graph it. There's the first half. Oh, there's the second half. Kind of looks a little bit like a heart. I think this one's called a cardioid. There's somewhere in the notes that I tell you they have special names. Okay, so what you're going to do is you're going to go through and you're going to graph the rest of these on your graphing calculator. Now, for the sake of our time on our video, here, I'll give you a rough sketch of what they look like. This one kind of goes like this. It has a loop-de-loop in the middle, like this little loopy thing. This one does curvy over here and then does like this little flat thing on the left-hand side. So it does a nice like kind of circle-y thing over here, but then it goes flat on the left. Those were all cosine examples. What happens if it's sine? Well, if it's sine, it does the same kind of thing, except now it's going to be around the, instead of it laying along the x-axis, it's going to lay along the y-axis. So this guy goes, whoop. Maybe it's a little bigger or smaller, it doesn't really matter. And then this one does the little inner loop thing. But again, laying along the y-axis. And then this guy does his little flat thing. The flat thing's down here. So this is the flat part. And then it curves and goes around the rest of the way. The picture on the calculator is way better than that. That looks really pretty sad. Okay, so the questions now with these graphs is which ones go through the pole? All right, so well, the pole is where the origin type thing would be. This is the pole. This one goes through. This one goes through. That one does not. This one goes through the pole, and this one goes through the pole. So my answer for this part of the question is my 2 plus 2 cosine of theta, 1 plus 2 cosine of theta, 2 plus 2 sine of theta, and 1 plus 2 sine of theta. Which do not? Well, 2 plus cosine and 2 plus sine. I'm just kind of putting them right under the thing here. What causes the graph to go through the pole, and that is when your r equals 0, right? Because that's where it is. You're talking about the radius being 0. It's going through the pole. And so r equals 0 causes the graph to go through the pole. Makes sense. Which graphs have an inner loop? Well, we saw those. Those are the 1 plus 2 cosine of theta and 1 plus 2 sine of theta. Which graphs do not have an inner loop? Well, the rest of them, we can list them, but I'm going to come again for the sake of video. The rest. And then what causes graphs to have an inner loop? They happen when when you have a negative r. When your radius comes out to be a negative number, the values, because you're going backwards, so negative r values cause the inner loop. And how did we say this one to make a full graph? A full graph took not 0 to pi. This time it went 0 to 2 pi. It took 2 pi to make these a full graph, a closed and enclosed graph. All right, onward to more pretty pictures. Here goes. Graph the following, sketch the graphs below, answer the following questions. All right, so again, for sake of time, here's what they come out to be. You can put these in your calculator, you'll see. And again, these are sketches. I am so not the best of artists here. Here's the first one. All right, let me again, for sake of time, let me give you this. Okay, so here's what they actually look like. You have 3 petals. See how it kind of looks like a flower? This one gives you 5 petals. This one gives you 7 petals. I had a hard time drawing that. I had to erase that one a couple times. This one also does the same thing, except see how it's oriented a little differently. This one has a petal that's directly on the x-axis. This one has a petal directly on the y-axis. Cosine, sine, okay? And then the rest of them go from there. So this is the 5-petal guy. This is the 7-petal guy. And so it took me for this one, now you didn't have to change your window, but I can tell you to graph these, you only had to go between 0 and pi. It would have graphed the picture for you on the calculator because you have it going between 0 and pi. It just would have traced over itself twice. So here's some things that we know about this. So what patterns do you notice? What patterns do you notice? There's Levi making his presence known. Let me put here a full picture, full graph. This time goes from 0 is less than or equal to theta is less than or equal to pi. It only takes that much to be able to graph these. And again, your calculator is already in mode that it should have been fine to graph them. So the patterns we notice, and here's the deal. You might not catch this, but if it's odd, the coefficient on theta is the number of petals. Let me explain that in a second after I write it. The coefficient on theta is the number of petals. You might have caught that as you look at these equations. Like, let me go back to the pictures here. This guy here, he had 7 petals. What's the coefficient on theta? It's 7, right? This guy had 5 as its coefficient. It's got 5 petals. This guy had 3. It's the 3 petals. So it's a coefficient on theta that decides that. And if it's if that coefficient is an odd number, then that's going to be the number of petals that you have. And then the number in front, the leading coefficient, maybe I want to say, I'll call it the leading coefficient, the number in the very front. The leading coefficient is the length of the petal. They're the 2 things that go with that guy. Okay, here comes the next kind. Again, you're going to go to your calculator, you're going to graph all these pictures and see what these look like. Now, do these look any different than our last set? No, I don't know. Let's see. I have to, sorry, sometimes using these erasable pens, things disappear, so I'm going to fix my pictures. There they go. So you put these in your calculator. Oh gosh, he scares me. You put these in your calculator. Here's the graphs that you get this time around. All right. He's barking at the mailman, and I just closed the shade, so maybe he can't see out the window anymore and scare me. He's really a sweet dog. He just sounds ferocious. Okay. For this one, I'm looking at these 6 pictures, right? Same idea. I've got the petals on the flowers. It's just where they're located. These are kind of more vertically bound with our X and Y axis for this guy. And then it's just an increase in the number of petals. So this one had 4 petals. This one has 1, 2, 3, 4, 5, 6, 7, 8 petals. This one has 10 petals. So as I'm looking at this guy, actually this one has more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This guy has 12 petals. So looking at our numbers for these, and this works whether it's sine or cosine, how do you know how many petals you have? It's always going to be 2 times the coefficient on theta, right? This one is 2. 2 times 2 is 4. I have 4 petals. This one is 4. 4 times 2 is 8. I have 8 petals. This one's 6. 6 times 2 is 12. I've got 12 petals, and there you go for all of these. So things we notice, if it's even, if you have an even number in front of the theta, it's 2 times the coefficient on theta is the number of petals. And again, the number in front, the coefficient in front is the length of the petals. This one, it takes 2 pi to make these. Okay, that's the story with the pictures. Let's do some application stuff with this next. All right. Before we jump into the calculus, we're going to look at the polar coordinate system. We need to develop some proficiency converting back and forth between rectangular coordinates, which we're used to, x's and y's, to polar coordinates that are r's and thetas. So they remind us of a few things in here. If I'm trying to convert from polar to rectangular, I need to change the polar piece into an x coordinate and a y coordinate. So this would be r times theta. That gives you, and in this case it's r times sine, gives you the y coordinate, and r times cosine gives you the x coordinate. Now if you remember back in pre-calc stuff with the unit circle, if I have a coordinate, whatever that coordinate is, you get an x coordinate, you get a y coordinate. The x gives you, the first guy gives you the cosine, and the second guy gives you the sine, the y. Kind of fits that same scenario. So you know this already. This is now just putting an r with that. So y is r times sine. Cosine is x is cosine times, what am I saying? X is the cosine, so cosine times r gives you that value for x. The other thing they remind you of over here is Pythagorean theorem, the creation of the right triangle. So you know that r squared equals x squared plus y squared, and you also know that tangent is going to give you y and x. So it's kind of like you're looking at ways to convert things into either r's and thetas, or ways to convert things into x's and y's, depending on which way you're going. So here we go with some examples. Convert 2 5 pi over 6 to a rectangular coordinate. Well, you know that this is equivalent to r, and this is equivalent to theta in the polar world. So to get an x coordinate out of that, I go here, x equals, I need an x coordinate and a y coordinate in the rectangular system. I know that x equals r times the cosine of theta. Right, that's the rule. So in order to get that x coordinate, I need my r is 2 times the cosine of theta, cosine of 5 pi over 6. And so I go to my unit circle. Hopefully you remember the unit circle. You need to know that for Mr. AP. If I go to 5 pi over 6, it is the coordinate of 5 pi over 6. So it's going to be the negative square root of 3 over 2, comma 1/2. So this guy's going to be times the negative square root of 3 over 2. If I cancel my 2's, multiply that out, my x coordinate in the rectangular system is a negative square root of 3. But I'm going to do the same thing to figure out what the y coordinate would be. Remember, you need an x and a y. Same idea, r sine of theta. And so I get y equals 2r sine of 5 pi over 6. That would be a 1/2. And so I have y equals 2 times 1/2, or 1. So my coordinate in the rectangular system would be an x of negative square root of 3 and a y of 1. There's your coordinate. Okay. Next one, though, is totally different. This one, converting 3, negative 3 to polar coordinates. 3, negative 3, so I need an r and I need a theta out of this. Somehow I'm supposed to get an r and a theta out of this information. Well, I know that up here, r squared equals x squared plus y squared. We have an x and a y. I can figure out r. So r squared is going to equal 3 squared plus a negative 3 squared. R squared equals 9 plus 9. So I get r squared is 18, or r equaling plus or minus the square root of 18. Now, we go with the positive, it's a radius. So it's an 18 for this one. They just put it in the, you could also leave it, by the way. The square root of 18, I know you can simplify that into 9 times 2, so 3 square roots of 2. You don't have to go there. You can just leave it as the square root of 18. Mr. AP is okay with that. So I got the r piece. Now I need a theta piece. Well, the only way to get a theta piece from an x and a y coordinate is to think about tangent. So this one's going to be the tangent of theta equals my y over my x. Well, my y is negative 3 and my x is positive 3. And so where is the tangent equal to negative 1? There's actually two places that it equals -1, and that would be where you have, remember it's y divided by x, so on the unit circle, that would be the negative square root of 2 over 2 and the positive square root of 2 over 2. One could be the x or the y, however that works. So two locations. One location would be in quadrant 2. That would be at 3 pi over 4. And one location would be in quadrant 4, where they have opposite signs, and that would be 7 pi over 4. I can't have two different thetas, so now I've got to do some thinking to figure out which one it actually is. So the one that it actually is has to be located in the same quadrant area as this guy. Think about what quadrant he's in. If I plot the point 3, -3, where am I? And I would be in quadrant 4, which then helps me know which one of these I want to pick. My theta has to be in quadrant 4, so I'm going with the 7 pi over 4, and that's going to be r square root of 18, comma, 7 pi over 4. And there you go. You just converted one into rectangular and one into polar. Let's try the next one. Converting the following equations from rectangular to polar. Well, what's another way I can write y if I'm trying to go polar? And another way to write y is to do r sine of theta equals 2 times, another way to write x is r cosine of theta plus 1. I need to know what r is. I need to know what r is. So I'm going to take this thing and I'm going to just do my algebra out to this. So I have r sine of theta equals 2r cosine of theta plus 1. I'm going to bring the r's to one side and leave everybody else on the other side. So r sine of theta, he's already there, minus 2r cosine of theta equals 1. Solving for r, I want to know what r is. Factor it out. Sine of theta minus 2 cosine of theta equals 1. How do you solve for r? Divide by the hot mess of parentheses. R equals 1 over the sine of theta minus 2 cosine of theta. That's it. You now have an equation that has r's and thetas in it. No x's and y's. All right, so next one. Y equals 4. What can we call y? In the polar world, we call y r sine of theta equals 4. Solve for r. R equals 4 over sine of theta. And you are actually done because you now have an equation that has r's and thetas in it. No x's and y's. And C is even easier yet if you can think about remembering the formulas, right? So x squared plus y squared equals 16. You don't have to go through this thing and change this to r cosine and r sine. All you need to do is remember that this is representative of x squared plus y squared equals r squared. So what's r? R is the square root of 16, which is 4. So my answer for this guy is r is 4. There is no theta involved. This is actually the equation of a circle whose center is at the origin and has a radius of 4. All right, there's some conversions. Let's try something else. More conversions, actually. Convert the following equations from polar to rectangular. Now this is, in this case, I want to get this into the rectangular. I need x's and y's. Now this one's going to be a little bit goofy. This one's a little bit trickier. You got to play a little bit more games with this thing. I need to get this into an r cosine, right? So I need an r to come into the picture. So out of thin air, I want to multiply that side by r. And I'm going to say so. Because I want it to have an r cosine, because r cosine is what is equivalent to the x value. So can I just do that? Can I just pull an r out of the air and toss it in here and multiply it and get r squared equals 2r cosine of theta? And the answer is yeah, because remember algebra balance? If I do something to the left-hand side, I got to do the same thing to the right-hand side to keep balance. Same thing happens with this. So yeah, I can pull anything I want out of the air and multiply it on both sides. But in this case, I'm going to pick an r. Now this part here is what equals the x value. How can I change this r? This r is going to go and change, this whole piece here is going to turn into my x value. So really on this side I have, this is equivalent on the right to a 2x. That's good, because remember we went into x's and y's. How on the left can I change an r squared into x's and y's? And it goes back to that Pythagorean theorem, because what does r squared equal according to the Pythagorean theorem? X squared plus y squared. So you see now I've got it into this equation that is x squareds and y squareds. Now there's different forms that this could take at this point. The way that the curriculum went, sometimes you know how this could be a multiple choice answer. This might be your answer right here, but you also might have to do something like this. So again, this is a valid answer. You got it now in terms of x's and y's. That's all wonderful. If I were to do this, x squared plus 2x, bring the 2x, actually minus 2x, right? Bring the 2x over, minus 2x, and then just bear with me, I'm just going to show you how this goes. Equals, and I'm going to leave a blank there. What they want you to do is complete the square on this and write this a little differently. Now if you remember how to complete the square, completing the square is take half the middle term and square it. Half of -2 is -1. -1 squared is 1. I add 1 to that side of the equal sign and 1 to that side of the equal sign. And then the deal is, can I factor that into a grouping? And the answer is yes. So here's another alternate form you might see. X minus 1 squared plus y squared equals 1. So the book actually took us to this location, which is an equivalent form to this. So again, it could be a multiple choice question with either of those things. Just kind of throwing it out there, showing you some extra stuff. Middle one, B. Theta is 3 pi over 4. Well, if I've got the angle, the only trig function that relates with x's and y's is tangent. So let me think about the tangent of 3 pi over 4. Thinking about that in terms of it being the y over the x. Well, go to 3 pi over 4 and figure out the tangent. We just did that a couple minutes ago. The tangent of 3 pi over 4 is a coordinate that is negative square root of 2 over 2, comma, square root of 2 over 2. That would be a -1. Equals y over x. And again, you can put this in different forms. A lot of times in the rectangular system, we would solve this for y. So if I did that, y would equal, cross multiply, a -x. There's your answer. All right, next one. R cosecant. Well, cosecant 1 over sine, right? Remember those reciprocal guys? If I cross multiply now, look at what I have. Woohoo! R sine of theta equals 1. Well, what's R sine of theta equivalent to in the rectangular world? And that would be your y. This would be y equals 1, and you have now converted that into the rectangular world. Okay. We have 2 last examples. They're a little long. I'm trying to make this as fast as I can. These are taking derivatives of these things. Okay, so that if you're looking to find the slope of a tangent line, that's normally how they put this. They want to know what the slope is or what the derivative is. The derivative for these guys is the derivative of dy over d theta divided by dx over d theta. We kind of saw that in the last section. I want to say in section 16.1, I think I remember us talking about that. And that converts to this if you needed to. I don't know. Are we going to get to this one? I'm not sure. R cosine of theta plus R prime sine of theta over negative sine of theta plus R prime cosine of theta, provided that dx over d theta is not equal to 0. That would give you a 0 denominator. Or you can create functions for x of theta and y of theta first, and then find y prime of theta and x prime of theta and divide them. That's the method that we're going to use more often, that last little bit. All right, so let's see. Find dy over dx. Notice dy over dx, and I'm given the polar curve in terms of r's. So this is really what I'm looking at here. I want to know the derivative of y with respect to theta and the derivative of x with respect to theta. And then they want me to evaluate it in the end for what is it at pi over 2. So you're not done at the very end when you find the derivative. You got to plug it in, plug it in. All right, so let me see what I've got here. I have 2 plus 2 sine of theta at the theta being pi over 2. So when you're trying to find, here's what we want to do to get the x. I need an x equation and a y equation. I want to know what x prime. I'm going to find x prime first. X prime of theta, I'll even be more specific. I want to find x prime of theta, and then I want to find y prime of theta. And then I'm going to divide them like it says, okay? So here I go. In order to get to in order to get to an x, if I have an r here, remember it needs to be r cosine in order to be an x value. So I need to take this thing and multiply by cosine. So for these guys, you're going to multiply by cosine. Here's what's going to happen. If I take my equation and I multiply by cosine on the left, I'll have r cosine of theta equals, I should maybe put the theta there, equals, and if I take this side and multiply it by cosine, it'll be cosine times 2, so we say that's 2 cosine of theta, plus 2 sine of theta cosine of theta. Right? Everybody's got to get multiplied by the cosine. Well, that's nice because now I can call this an x equals this equation, 2 cosine of theta plus 2 sine of theta cosine of theta. Now, can you find me the derivative, x prime? Sure you can. We know this. If I do x prime, then the derivative, now remember we're going derivativing and not integrating. So derivative of cosine is negative sine, negative 2 sine of theta plus, actually this is a product rule. The 2's out in front. I'm going to put the 2 in front, I'm going to bracket it, and I'm going to product rule that. So it's the first times the derivative of the second. Derivative of cosine is negative sine, plus the second cosine times the derivative of the first, which is another cosine. And so I'm going to see if I can simplify this a little bit more. X prime equals, can't do anything with my negative 2 sine of theta. This guy would become 2 parentheses, actually a negative sine squared of theta plus a cosine squared of theta. Now I can keep going with this. I can keep simplifying it out more and more. Maybe I'll take it one more round. X prime, negative 2 sine of theta minus 2 sine squared theta plus 2 cosine of squared theta. And that's probably where I'd leave it. They want to know what's it doing at pi over 2. So now I want to know what's x prime of pi over 2. So once you find your derivative, we want to figure what that value actually is. So go to pi over 2 on the unit circle. It is the coordinate 0, 1. And so I am going to put in a sine of 1 and a cosine of 0. Here it goes. This is going to be a 1. This guy's going to be a 1. And this guy's going to be a 0. So what's that going to give me? Negative 2 times 1 is negative 2. Negative 2 times 1 gives me negative 2. And 2 times 0 gives me 0. And so out pops a negative 4 for that value. We're halfway there. Because now I need to do the same thing, exact same stuff for finding y prime technically of pi over 2. So I'm going to this time think about what you're going to multiply this time to get the y. I'm trying to turn it into an r sine of theta, right? So if it's r sine of theta, I've got to multiply by sine of theta. Here it goes. R sine of theta equals 2 times the sine of theta plus 2 times sine is sine squared. Well, that's what y equals. I'm going to write this a little slightly differently. Same thing, remember, sine squared is the same thing as taking sine and squaring it. But I know I'm derivativing, so I might as well put it in a form I like. Derivative of sine is cosine, 2 cosine of theta, plus, in this case, the 2, remember, power comes down in front, becomes a 4. Take the grouping to 1 less power, and then take the derivative of what's inside, and there you go. Little chain rule thing going on. Well, now I need to put in what is it at pi over 2. So that's going to be 2, I guess I didn't write it this way on the other one. Same idea. 2 cosine of pi over 2. You get the concept. 4 sine of pi over 2, cosine of pi over 2. And so I go to my unit circle again and figure out what these values are. Cosine is the x, sine is the y. And so I'm going to figure this value out. Well, 2 times 0 is 0, plus 1 times 0 is 0, and I get a whole lot of nothing. And so the question wants to know, what is dy over dx? And we say y is 0. We say that dx was negative 4. When I divide them, I get 0. How about that? All that work to get an answer of 0. Welcome to the world of calculus. So what we really did was we created functions of x of theta, y of theta first by multiplying by either cosine of theta or sine of theta. We found the derivative of each of those, plugged in the theta value, and then we divided them, and that's our answer. So that's the deal. Here comes the last one. Again, it's a long one, but it's not horribly, terribly horrible. Okay, so this one, they want example 10, find the points r theta, polar world, of horizontal and vertical tangency to the graph of r equals 2 cosine of theta between 0 and pi. So you got to think about when vertical tangency. When is your tangent line horizontal? When is your tangent line vertical? You know that the slope of your tangent line, can you see me? Yes, slope is equal to whatever, in this case you've got your y prime over x prime, right? The slope is the derivative, y prime and x prime. dy over dx, however you want to write it. It's all one and the same kind of thing. So it's going to be horizontal is the first one they do, so let's do horizontal. They asked about that first. It's going to be horizontal when looking at your fraction, when your numerator is 0, when you've got a 0 slope, 0 over a number. So when y prime equals 0, and it's going to be vertical when it's undefined slope. Undefined is when the denominator equals 0, so x prime equals 0. Well, that means that we need to find them, right? So to find where it's horizontal, I need to find where y prime equals 0. So I'm going to take my equation, here it is, and what am I going to do first? To be able to find the y equation, I need to get it into an r sine of theta. So I'm going to multiply, I'm going to go horizontal first. I'm going to multiply by the sine of theta. So I can get into a form that's y equals. So that's going to give me r sine of theta equals, what do I have there? Multiplied by sine, so 2 sine of theta cosine of theta. Well, r sine of theta is y. There we go, good. 2 sine of theta cosine of theta. Take the derivative, I need y prime. Where is y prime equal to 0? Y prime is going to be, product rule, sine times the derivative of cosine, we just did this a second ago, negative sine, plus cosine times the derivative of sine, which is cosine. That's a C. That's a horrible looking C. Okay, anyway, y prime equals 2 times a negative sine squared theta plus a cosine squared theta. All right. Now here's the issue. They want us to find the points. we've got to figure out what the actual coordinates are for this. And so this is not that. This is an equation where you can find those things, but this is not a flat out answer for, remember, it has to be an R value and it has to be a theta value. Find the points R and theta. So here's what I have to do. I have to pull out from my toolbox things that we learned back in pre-calc, and hopefully you remember some of these. Watch and see. There's another way that I can write cosine squared theta, and it's based off of one of your Pythagorean identities that says sine squared theta plus cosine squared theta equals 1, if you remember that Pythagorean identity. Mr. AP assumes that you remember that. All right, so what does cosine, can I replace this so that I have it all in terms of sine? So I'm going to go with, now I could have replaced this guy, but he's negative, and then that gets a little hairy with the negative sign. So I'm going for the guy that's positive, and I'm going to change him. So that means cosine squared from this equation would be equal to 1 minus sine squared if I manipulate it. And that's what I'm going to do. I'm going to take and I'm going to replace this, maybe I'll keep it in my red here. I'm going to take this cosine squared and I'm going to replace it with what cosine squared equals according to the Pythagorean identity. It's going to look like this. Y prime equals 2 times negative sine squared theta, that's this part here, but I'm changing this to this, plus 1 minus sine squared theta. And I'm going to see if that does me any happiness here. So let's see, I have a negative sine squared and another negative sine squared. I can put them together. 2 times, and I'm going to put it this way, 1 minus the sine squared theta. And that's not true, right? I need a 2 here. I have 2 of them. 1 minus 2 sine squared thetas. That's better. Now if I distribute the 2 out, I get y prime equals 2 minus 4 sine squared theta. And I'm getting closer to the end of this thing. Good thing they gave me a big old page. All right, so I want to know when it's horizontal. That's when y prime equals 0. We said that all the way back at the top, so set that equal to 0. 2 minus 4 sine squared theta. I need to solve that. Ooh, the 2 swings over. Negative 2 equals negative 4 sine squared theta. The 4 gets divided. Negative 4 into negative 2 gives me 1/2 is sine squared theta. All right, now I need to square rooty to get to the sine of theta. Square rooty. And I end up with the sine of theta equals the square root of 1/2. Let me do it this way. Square root of 1 over the square root of 2 gives me 1 over the square root of 2, gives me the square root of 2 over 2. And the reason I want to keep going with that is because I need to know where that is on the unit circle. So I need to get it into a format that's on the unit circle. And I know that there's 2 locations where that happens. Where the it's a square root, it's on any of your pi over 4s. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. It's one of your quarters. That's going to give you want where the y value is positive. So that's going to be in the first quadrant, which is pi over 4, and in the second quadrant where it's a positive y value as well. So this would be at 3 pi over 4. Well, now you got your theta value. What do you need to put it into the coordinate system? You need an r and a theta. All right, well, here we go. We got to do each of these things and put it in and figure out what the corresponding r value would be. It's going to give us 2 different points. So if theta equals pi over 4, then r is going to equal, go back to your original equation, it's 2 cosine our angles pi over 4. What would that be? 2 times, this would be the square root of 2 over 2, and that equals the square root of 2. So this coordinate would be r, square root of 2, theta, pi over 4. If, I'm going to have to probably move my paper, if theta is 3 pi over 4, same thing I want to do. I want to figure out what the corresponding coordinate would be. So it's going to be r equals 2 cosine of 3 pi over 4, which happens to be a negative square root of 2 over 2. So 2 times negative square root of 2 over 2 gives me a negative square root of 2. Here's my coordinate. I'm just going to put it right in there. Negative square root of 2 when it's 3 pi over 4. Woo! That's when you've got horizontal tangents. But wait, there's more. They want us to do it for verticals. Now this one's shorter. It's not as quite as long. All right, here comes. Vertical is when x prime equals 0. We need to get to x prime. Right now we have to multiply. This is for vertical. We want to multiply to get it into an x thing, which is going to have to be a cosine. Multiply by cosine of theta. Here it goes. R cosine of theta equals 2 cosine squared theta. Each side gets multiplied by a cosine. This becomes an x. Right-hand side stays the way it is. Now I'm going to put it as cosine of theta quantity squared because I'm going to have to derivative it. So it helps me to see that power rule better. So here I go. Here's x prime. 2 comes down, becomes a 4. The cosine goes to 1 less power, so it's just the first power times the derivative of what's inside. That's a negative sign. So I'm going to put the sine of theta here, and I'm going to put a negative in front of the 4, just for the sake of not having to rewrite it again. Now I need to set this x prime equal to 0, so that gives me 0 equals negative 4 cosine of theta sine of theta. Well, divide by negative 4, right? It's attached by multiplication. I want to get rid of it. I'm dividing by it. So it's going to be 0 equals the cosine of theta sine of theta. And you say, oh my goodness, I'm not quite sure how to solve that. Well, think logically about this. In order for this to equal 0, either cosine is 0 or sine is 0. So it's kind of more of a logic type thing. Here you go. Cosine of theta equals 0. Sine of theta equals 0. When that happens, when one of them happens to be 0, the whole thing's going to be 0. So then I'm looking at my unit circle and I'm figuring out, well, where the heck is the cosine equal to 0? Well, that would be, and I'm only staying between 0 and pi because of my directions at the top, that would be at pi over 2. That's at the top of the unit circle. That's the coordinate 0, 1, x value is 0. Where is the sine 0? Well, the sine is 0 at 0. When my y value is 0. All right, let's figure out the r values that equate to these. So if theta is pi over 2, then I'm looking for my r. R is going to equal 2 times the cosine of pi over 2, my original equation. Cosine of pi over 2 is 0. So this thing equals 0. 2 times 0 is 0. And so this coordinate is going to be 0 pi over 2. If theta is 0, then my r is going to be 2 cosine of 0. Cosine of 0 is 1. 2 times 1 is 2. My coordinate's going to be 2 comma theta of 0. All right, that completes our polar stuff. Let me just give you some heads up about homework problems that go with this, because there are ones to skip. Okay, I'm looking at this and giggling because look at number 6. It got all like erased somehow in the midst. I hope I scanned this. I think I did before it got erasable. Number 8, you are skipping. That's the first skippage. Skip number 8. All of this is number 7 when I did this. It's one of those where you have to figure out the x and the y and such. So that you're skipping. You are skipping numbers 10 and 11. 10 and 11 on the flip side. On 12 to 15, you are graphing these guys in your calculator. Don't have to make a table. You're just doing. I talked about how to do a table, but you don't have to do that. And I gave you the mathematical names for these things just so you could, for the kicks and giggles. This guy is called a cardioid when it doesn't have the loop-de-loop. This is a limison, and it has this really weird C with a thing underneath of it. That's when it's got the loop in the middle. This is a rose curve, looks like a flower. And this is a limnoscate, when it looks like an infinity sign kind of thing. So just special names. You can graph them, you'll see. And then there are 3 multiple choice questions, 16, 17, 18. They're good to go. Okay, so I will see you in class and be happy to answer any questions you have. By the way, there are some optional assignments beyond that. Obviously, with our time frame, I don't expect that you're going to do them, but they are there, and the answer keys to them are also included, so it's on our classroom page. So the parts that you have to do are up to number 17? No, 18. So you're doing 1 to 18, but you're skipping the ones that I just said. All right, sorry it's so long. I will see you in class. I hope I didn't put you to sleep. Bye.